Hello, and I must thank the organizers for having me here, and I'm able to talk about this. So it's more of an experimental-oriented talk, and I have intentionally kept it quite open-ended because after taking some years from research, I'm not now just getting back to some open questions that I'm really interested in. So I'm going to talk about the possibility of accessing optically some specific kind of topological phases in certain sort of spatially indirect excitons. They are confined in quantum systems. So the motivation lies in the fact that while topological phases are quite well established, and in electronic systems they have been studied largely since a long time, and often in mesoscopic quantum ring sort of systems. But however, in neutral excitonic systems, they remain largely unexplored for obviously technical reasons. The question that whether topological phases such as the Aronoff-Bohm phase, it can be experimentally measured and eventually be harnessed to kind of store light and release it on demand, like externally controllably or not, is my core question here. And I'm going to talk about it like showing two parallel systems which are kind of showing possibility of doing so. The idea is that this whole point is very interesting because if we have strong many-body interactions, reduced dimensionality, and high optical accessibility, what we probably need is just like in Professor Arundam Ghosh's talk and today Subrata's talk, that you need clean systems where you can actually do it, something of that sort, which are quite subtle they are inscribed in the system. So a brief outline is, and I have to probably brush off a lot of things. I made this talk mostly, thank you, for the students here. And so probably, but I see that I can probably skip on the theory of it quite a bit, and I'll straight away get into the observation of excitonic Aronoff-Bohm effect in a specific type 2 quantum dot systems that I have worked on, and most of those experiments were done at the City University of New York and National High Magnetic Field Laboratory in Florida. And later on in the second part, I want to kind of show the scope of investigating a similar sort of approach in 2D, two-dimensional van der Waals heterostructures. So, and especially I'll kind of try to propose a protocol for Moire-trapped excitons, which I think have the genuine possibility of observing such effect there. So I will probably skip this. The seminal work by Aronoff-Bohm in 1959, talking about the significance of vector potential more than just as a mathematical jargon, and that was later on closest experiment that was done later on in 1986, which was any close to saying that, okay, there is proof. And I love to quote Richard Feynman, the fact that the vector potential appears in the wave equation of quantum mechanics was obvious from the day it was written. It seems strange in retrospect that no one thought of discussing this experiment until 1959, when Bohm and Aronoff first suggested it and made the whole question crystal clear. So the physics community was kind of divided in two for when this particular theory was proposed, and it still remains quite elusive sort of experimental things where we can actually probe this, for example. So I'll just start with the generic picture of a magnetic Aronoff-Bohm effect. You have a solenoid current carrying, and the field outside the solenoid is zero while the vector potential is not. So if you have two electron paths traveling across in opposite directions, there will be accumulation of a Berry phase or an Aronoff-Bohm phase, and you should be able to, in principle, observe some interference effects if you're able to experimentally probe it. The origin is similar coming from the adiabatic theorem, where you have adiabatically, if you evolve a Hamiltonian from a state Hi to Hf, eventually it will be carried into the there will be some geometrical phase factors that will be coming along with it after the evolution. So for the electron path coming from this side and for the electron path coming from this side, they will be slightly different, and that delta phi can be, in principle, that exists, and in principle it should be accessible or measurable in some ways. So now I'll go straight into the approach of where they start talking about an excitonic Aronoff-Bohm effect, where an exciton is a electron and hole pair. They are bound by Coulomb interaction. And essentially the picture is quite straightforward to think about. In this case, we are not going for zero magnetic field, however. We are going for finite magnetic field, and you are exposing the whole system to the magnetic flux. And what happens is when, after a complete rotation, the electron and hole, they are taking two different trajectories. So the magnetic flux line, there is a difference in this area of this two trajectories, and essentially it is coming from the interaction of the electric dipole with the vector potential, and you should be able to observe that the phase accumulated by the electron and the hole after a complete revolution is actually different, and that you should be able to observe experimentally. The core idea is that depending on the electron and hole coupling, different observations were predicted by some theorists back in the early 2000s, and this was one of the simplistic picture we can look at, and I'm now taking in account, suppose you have a system where the hole is strongly confined and the electron is moving around it, so that we can just look into only the electron's orbital momentum. It turns out the excitonic energy, as you increase the magnetic flux, will go through for different angular momentum states. It has different evolution pattern. And you will see that for L equal to 0 to L equal to -1, the black and red curve, at certain point, at the transition point, it will go to L equal to -1. So there will be an angular momentum transition happening because it's lower energy state. And what we are trying to probe here is, optically speaking, when you have an excitonic emission, it is governed by optical selection rules, and there you can go from bright to dark excitonic states. And if you have such a system where you have both electron and hole contributing, you can get multiple oscillations in the photoluminescence or intensity and energy for excitonic emission. And largely following this theoretical work, Igor Kuskovsky back in 2007 kind of showed the first optical signatures of seeing such effects. Now I just need to go a little bit in the material side so we can think about how it is relevant here. So not spending too much time, type 1, type 2 band alignment of semiconductor heterostructures, where you can have in such a configuration in type 2 band alignment where the electron and hole, they are going to sit in two different materials. So you are having spatially indirect excitons. And that results in certain sort of effects, optically speaking, that you have much longer carrier recombination lifetimes. Also, there is one signature effect of having such type 2 excitons is that when you photoexcite the excitons and create them, at the interface you create this band bending, and that is largely accessible by applying external fields, electric, magnetic, and all that. So particularly speaking, I worked on this type 2 zinc telluride, zinc selenide stacked quantum dots, where you have such a very similar configuration, and the band offset is very high for the hole where it is comprised inside the zinc telluride layer. So the hole is strongly confined, just as in the cartoon I showed you before. I do not have the time to go into a lot of details about this, but the samples were grown by Professor Maria Tamargo by using a combination of molecular beam epitaxy and migration enhanced epitaxy, where you can, with a very sophisticated shutter sequence, kind of control the distribution of the quantum dots. And they are not ever forming a full monolayer. It's always like sub-monolayer quantum dots, and they're quite hard to be imaged. This also, there are some signature studies like enchilada of optical experiments where you will know this type 1 to type 2 band alignment, and you can observe this sort of energy behavior of the PL peak as a function of excitation intensity, where it tells you that it's a type 2 band alignment. Also in time resolved measurements, you will see such long, of the order of hundreds of nanoseconds decay times. So interestingly, we observe for various samples in the same set, like with different sort of growing parameters, we get different sort of, the PL itself indicates what are the recombination centers and what are the different kind of excitons. For example, the ones in the lower energy side, they are dominated by quantum dot bound excitons, and the ones with the sharp lines, they are the phonon replicas, and they also have the defect bound states which are near the zinc selenide matrices. And by time resolved photoluminescence, you can identify and sort of describe each of them quite directly. So now I want to come back to the magneto-optical studies where this Aronoff-Bohm effect is more pertaining, and in this context, the model is kind of simplistically made here. So we have stacks of zinc telluride quantum dots where the hole is strongly confined, and not all of them are populated. And we have the electron, which is kind of on an average going around in with respect to the whole stack. This model is kind of experimentally supported by high resolution XRDs, where we could see very strong correlation, vertical correlation in these samples, up to about 75 to 80%. So you can consider that these are like, seems like cylindrically stacked quantum dots. So it kind of gives it this enhanced cylindrical symmetry, which is also kind of conducive for observing such an excitonic Aronoff-Bohm effect. From the simplistic picture, you can actually, if you happen to observe the Aronoff-Bohm oscillation, you should be able to calculate the lateral excitonic size or the lateral radius of the exciton using that. We kind of did some work in that, and I just want to quickly show you some of the real experimental data that we had in that regard. So we could observe for various samples that our transition field was around 1.9 to 2.5 Tesla. And also another important aspect we realized was, because these are quite strained and asymmetry is there, so we often get a lot of, there is a built-in electric field that comes in play, and which actually aids this effect, and that's why we observed probably one of the most high amplitude AB oscillations reported for so far. I mean, optically to detect it also is kind of a tricky experiment. There is another very good work, theoretical work, that was proposed by Fisher et al. In 2009, where they talk about a protocol where you can actually use this sort of scenario into creating the exciton and storing it and retrieving it at your will. And I probably will go to that at the end if I have some time. Also, a very simplistic approach that could have been taken is by using the AB peaks position and its nature, we could, in principle, distinguish different stacks of quantum dots which were available in these quite complex systems, you would say. And we could, in fact, once we were able to resolve these transition peaks, you are able to also determine this electronic orbit with sub-nanometer precisions. And I would say that is just like a side game for it. It's not really the main goal of doing such a work. But essentially, if you go on and do some time-resolved measurements, and you are able to also support the same results, essentially, that you are able to look into the different quantum dot stacks. And a spectral analysis can kind of become a tool for these this rather non-imageable sort of submonolar quantum dots. So I'm skipping this data because I really want to spend a little bit more time in the open questions and what I'm proposing as an idea here. So I'll just, another important aspect is the energy oscillations, which you also should observe. And they're kind of rather elusive experimentally so far. But we could observe very distinctive energy oscillation behavior. And we believe that it also had to do with, because these are not single quantum dot systems. They're like, it's a system and of quantum dots and also defect bound states. And those happen to show up, and there are like, near the transition field, we also get like this anti-crossing sort of behaviors, and like there are bands of energy states that we believe are, and we are still working on the, making a theoretical model for this this work, but it happens to be that we do observe very clear energy oscillations as well. The tricky part was to do magneto-time resolved experiments, and the resolution was not so good, but eventually we were able to see the direct influence of lifetime near the Abbe oscillations, and it remains quite difficult to kind of run these experiments. And the bottleneck is that there are incoherent contributions that's always like diffusing out the Abbe effect as a whole. One extremely interesting aspect will be to see that how we were able to access the decoherence mechanisms all optically. Because as Arindam Ghosh also said in the review talk, the biggest problems when we create this for transport measurements is making the contacts and like making sure that for most of these systems that we are not creating extra effects. But here we could do by tracking the temperature dependence of the Aharonov-Bohm peak over from 0.3 Kelvin to here I'm showing until 27 Kelvin for this particular system. We could actually model it, and we could get into a functional temperature dependence where we could see that the T to the power -1 was electron-electron interactions, and there were smaller but exciton-phonon coupling was also present. And this can be a very interesting direction, I would say, apart from the spectral studies, that we are able to investigate all optically what are the decoherence mechanisms, and it becomes very interesting for newer systems as well if you're able to access this. Another important aspect was to look into these defect bound states which are coming from this higher energy side, and we could observe in this magnetic field, we could observe in millikelvin temperatures that we are getting very nice and sharp peaks. And this is actually unpublished data. We are working on it at this point of time, and this is something which is crucial to understand, that if defect bound states are also able to host Abbe phase trajectories in a similar sort of geometrical configuration or not. For all the sharp lines that we see here, we could do this temperature dependent, like at 400 millikelvin, we could do this measurements where we could see that all the additional features are present in sharp line region as well, which is kind of interesting considering that to understand the geometrical trajectory of the electron and hole excitonic configuration, it remains kind of important. We are able to look into this, but all of them showed experimentally this. So we are in a point where we are trying to model it theoretically. How much time do I have? Because I need to kind of tune this. 7 minutes. 7 minutes? Okay. So I'll probably brush this off. I just wanted to now open the floor for how I want to extend it into this 2D material regime. So one thing is that this is some work that we don't have time to talk about, but essentially it's we can use 2D materials and on photonic beds, some sort of photonic environment, and we are able to tune their intrinsic properties. One thing that was done recently is that we could tune the linear polarization of the excitonic emission by putting a passive plasmonic atmosphere around it. And that was a very interesting work, because essentially now I want to extend this idea into how we can access this sort of topological phases in moire-trapped excitons in 2D van der Waals heterostructures, which is rather relevant to this particular conference here. So essentially, the idea remains the same now. We have electron and hole pair, which is the exciton, and they're in the moire, it's this cartoon figure, we can assume that essentially you have the same path difference mechanism which is underlying as we parallelly from the quantum dot platform. And the spectroscopic methodology to how to study it can be kind of borrowed from there. And the idea is that can we create this close, because in a Moire trap system also you will have interlayer excitons, intralayer excitons, but as long as there is some overlap of this electron and hole wave function, and as long as you are able to apply a magnetic flux through it, are you able to access a similar sort of behavior or not? Now, we already have fabricated these van der Waals heterostructures, which are like bilayer twisted tungsten diselenide on top of each other. And this Moire engineering also gives you a tunability of how much the quantum confinement is. So that is also one of your tuning parameters. And essentially, the idea is that now we want to create this excitonic ring trap and see if we are able to access that or not. We apply synthetic magnetic field, and of course, we will need to do similar sort of optical measurements, and also if we can devise some interference fringe shift experiments or not. So this is a real sample that was created and by Ursula Wurzbauer at University of Münster, where we have tungsten diselenide encapsulated in boron nitride. It's a bilayer, and we could tune it from about 0 to 8 degrees, and it does have like a certain few challenges that there is a gradient of the Moire potential across a particular twist angle sample. But essentially the idea is if we are able to go and look into the same, with the same information that we have so far, that we will need to ask what is the Bohr radius of Moire trapped excitons, and if the interlayer excitons, if it's within reach experimentally or not, if we do a similar experiment. The spatial indirectness is the key for this whole experimental idea. And although we also have to note that these 2D materials, they already have an intrinsic Berry curvature, non-zero Berry curvature, and valley properties, which are also accessible. But that's by itself is very interesting to study in more detail. But if we just take in account the spatial indirectness, are we able to access the Aharonov-Bohm phase or not? And of course, some lifetime influenced to see and extract the different sort of different kinds of excitons in these systems, which also remain to be explored for this particular context. So there are going to be many bottlenecks probably, and that you have multiple excitonic contributions, weak coupling to no coupling to magnetic flux or not. So these experiments remain to be done. And probably one way to go about this bottleneck can also be to look into some photonic test beds, because we can create essentially these Moire photonic crystals where you can also sort of look into the topological effects there, and if there is a way to kind of connect them. Of course, disorder and localization and defect states are that will be relating to the defect states that we studied in type 2 quantum dots as well. And of course, phase readout difficulty. But all of these stands far, it's like far-fetched for now. We need to really do the preliminary experiments, which we are targeting with some collaborations and also some theoretical work. Nirmal is here. He's also interested in this problem, and we hope to get some more insight where we can give some more quantitative picture to it. My summary and outlook, I'm borrowing the slide from Fisher, where this is a very simple idea in some sense, that the y-axis is oscillator strength here as a function of magnetic flux quanta. So, and these are electric field applied in plane, in addition to the magnetic field which is applied in axial direction. So essentially you are able to tune the oscillator strength from with a protocol where you can go and make it finite and positive, where you are supposed to see you are able to create the exciton where it is ready to recombine, but by changing the electric field, you can bring it to zero, and essentially you stop it from recombining, external control. And at your will, you can play with in a magnetic and electric field, and you are able to switch between this storage and retrieval of the exciton externally controlled. So this will probably be a very good direction to look into if you are able to store quantum information, if you're looking at light as stored quantum information. So the field is huge. I think the open questions are many, and the Valley physics, Berry curvature for Moire systems, and using artificial lattices, and studying if spatially indirect excitons can be a good candidate for this remains my question here. So I will end my talk with that, and I want to thank a lot of people. Igor Kuskowski, my PhD advisor, we are still working on those data on the defect states which we are looking for. All these people, Maria Tamargo for samples, Vinod Menon for some of the investigations, Siddharth and Hauji, and John and Ursula in Germany. And most of this work were funded by NSF in USA and Alexander von Humboldt Fellowship in Germany. So so right now I'm looking into the open questions, and I love to have some discussions. Thank you.
Questions? So basically I was thinking this electron and hole exciton system making a path around some magnetic field, and then the effect when they recombine. Now their paths are different. Electrons and hole can have their own different path, and if the electron or hole have their own, due to the circular, for some reason like magnetization, or they have their own magnetic field, that will give in addition to the external applied magnetic field. Any comment whether this coupling is weak or it can be neglected, or it is not?
That will be one extra parameter to take care of. But theoretically speaking, nothing stops it, as long as the key idea is you just need to have this different two trajectories, so that you have it's like a ring-like trajectory area in the magnetic flux, which is really creating this. So your question is valid, but it will only complicate the thing. But as long as you have this electron-hole trajectory difference, nothing stops from observing it, as we can.
Depending upon the system where it allows the circular motions of electron and hole, the final experimental signature may be little different.
Correct, absolutely. Also, the fact is like this, how strong the coupling is kind of determines what sort of interference effect you will observe. Like what sort of angular, if at all, if you're having such angular momentum transition or not. So definitely, yes, the strength of the interaction, and as well as if you have any other sort of extra parameters, it both will affect it. Theoretically speaking, nobody stops it, but needs to be calculated properly to say anything conclusive. Yeah.
Any other questions? Okay, so Lord, please stand up.